Hi guys, in this very lesson on circular motion, we're going to be looking at the seventh and final worked example on uniform circular motion. We've worked on major six examples in our previous lessons, and today we are looking at the seventh and the final worked example on uniform circular motion. So if you think you could give this a try, I'll give you some time to do that right now. Welcome back, guys. Let's see what we have right here on the board. Now, suppose the Earth is a perfect sphere with radius 6,370 kilometers. The person weighs exactly 600 Newton at the North Pole. How much would the person weigh at the equator? Now, among all the formulas we derived in our previous lesson, we didn't derive any formula that looks like this. We derived a couple of formulas on, under uniform circular motion. We worked on, you know, the we worked on canonical pendulum. We worked on different stuffs, Ferris wheel, a body moving in a banked circular path, a body moving in a plain circular path. And we looked at a couple of things, but we never worked on something like this. Now, this is simply uniform circular motion involving, the gravitational field. So we're going to be doing a couple of quick derivation of formulas involving some of the, very relevant terms on this. So according to the great Isaac Newton, he put out a major law known as the law of universal gravitation. According to Newton, he said the force of gravitation, which sometimes can be likened to weight, is directly proportional to the masses of two bodies. We have the bigger body and we have the smaller body, and inversely proportional to the square of their distance apart. So when we have this, it means the force of gravity, we're going to take one of the proportionality constants, is directly proportional to the two masses, mass 1, mass 2, over the square of their distance apart. So we can bring in what we call a gravitational constant. So the force of gravity or the weight is equal to gravitational constant, the bigger mass, the smaller mass, over the square of their distance apart. Now we're going to be looking at gravitational field, in the next couple of lessons. So we're not going to be going too deeply into it. I'll just be showing you a couple of formulas that will help you understand what we're about to solve right here on the board. So according to Newton, what it simply says is simply this. Now, when we have two bodies, bodies with different masses, at a given distance, the fact is, the more the distance between these two bodies, when you look at it, since force of gravity is inversely proportional to the square of their distance, so it means the more the distance, the lesser the force of gravity. Why the lesser the distance, the more the force of gravity. We're going to be doing an in-depth study on this, when it's time to work on gravitational field. So now, quickly, let's look at this. The force of gravity is equal to gravitational constant times the bigger mass and the smaller mass over a square of the distance, apart. Now, the first thing we're going to be looking at quickly is what we call the escape velocity. Now, when we have a body like this, let me say we have the Earth like this. The Earth is not round. The Earth is, we call it, the Earth is an oblate spheroid. The Earth is spherical in a way. So what it simply means that at the pole, like this, at the pole, the Earth is flat, but at this very equator, at the center, it has bulges. So the Earth is not round. The Earth is like this, flat at the poles, and bulges with some rough, patches at the very, edge, just like this. So it's an oblate spheroid, flat at the pole, and bulges at the very sides, like this. So that's what the head is all about. That's what the head looks like. Now, when we have this, let's say we have a body orbiting the Earth like this. Let's say we have a body orbiting the Earth like this, moving like this. Let's say we have a body. Those bodies can be called satellites. And for the fact that we have a body orbiting the Earth, now there's a kind of we talk about circular motion. We're talking about bodies moving the circular path. So what really helps bodies to move in this very circular path, about this very Earth, to keep moving in this orbit, is simply the gravitational force. Unlike other stuff we talked about, other stuff we discussed different things that bring about centripetal force. But for this, what brings about the centripetal force, that is the force that keeps body moving in a circular path, is simply the force of gravity, which is as a result of the attraction between the masses of those two bodies. So now when we have this, now there is a given term we call escape velocity. As this body moves about about the Earth like this, let's say it's a moon or something. Now there's a force that is needed to break this body out of the circular path. That force is what we call escape. There's a velocity, I beg your pardon. That velocity is what we call the escape velocity. So now look at what we have. If the force of gravity is simply this, don't forget that the force of gravity is what brings about the centripetal force here, or the angular force, or sometimes you can call it the radial force. So if this is what we have a G m bigger M smaller m over r squared. What's the force of what's the centripetal force or the radial force or angular force? What's the formula? Don't forget that it is md squared over r. That's what we have. Don't forget that the acceleration is linear velocity times angular velocity. Linear velocity itself is angular velocity times radius. So we end up with when we have this, it means angular velocity velocity over radius. So you have v times v over r. We write this now previous lessons. So this is what we have. So what happens? So let's assume that there's a body moving around the Earth. Now the mass of the Earth is this big M, this big mass here. The big M represents it. The body moving about the Earth, that's in the orbit of the Earth, is a small mass here, which is seen as the small mass of the body moving times the linear velocity squared over radius. So this takes out this. What do we have? Let me bring it over to this place. We have the v squared over r equal to gravity m over radius squared. So what do we have? Even the r can come over to this place. That's the radius distance between the two bodies. So we have a g m times r over r squared. This takes out this. You have just one r left. So the escape velocity is square root of the gm over this. This one of the major formulas for this. Now there are a couple of other formulas we can derive, but I'm just trying to derive the major ones we're going to use to solve this. Now after getting this, now the next thing we're going to be looking at is simply this. Now imagine there is a body, and there's a human being standing here at this place. Now this is the center of the Earth. The center of the Earth is known as the equator. Here's the equator here. Here's the pole. There's a north pole. There's a south pole. Now, as you can see, this is the center. Now, a body standing here is very different from when a body stands here, when a body stands at the equator. When a person stands on the pole, either on the north pole or on the south pole, it's entirely different from when that person stands at the equator. Now, when this person stands on the north pole, as you can see, the distance between the very person, this object, it could be a person, the distance between this very object and the surface of the Earth on the North Pole, there's no distance. This person is directly on the surface of the Earth. Unlike when this person is here. When the person is here, if you look at the distance from here to the equator, as you can see, it's a given distance. And that's why the radius, this is the center of the Earth, the radius of the radius of this very Earth is varies depending on where the person stands. As you can see, the 6370 kilometer is from the equator. So now there's it here. As you can see, this place is flat, and here also is flat. So you cannot expect the same radius with this place. That's from this place to this place. So the radius from here to here is a bigger radius compared to the radius from here to here, which is a smaller radius. So we're going to be looking at what we're going to be looking at the kind of force, the kind of gravitational force that will be involved when a given body is on the poles and when a given body is at the equator. That's what we're going to be looking at quickly. We're going to be looking at that. So as you can see, it is force of gravity that brings about the movement of this body in a circular path. So that simply means the force of gravity. Now we are looking at when the body is at the pole. When the body is at the pole, that's what we're looking at. So when the body is at the pole like this, the force of gravity will try to help this body to keep maintaining movement in this circular path. Most times, that very force, force you're talking about is equal to the centripetal force as a result of gravitational force, overcoming simply the weight of the very object at that very pole. So when the two of them react, you have a body at this very point. This very body here is at a kind of what we call weight. It's a downward weight. It's a downward weight. So why force of gravity, fights against this very body to keep this body moving in a circular path. So this is what we have here at the very pole. This is what we have at the very pole. The force of gravity minus the weight of the body, which is often mass and gravity, is to bring about what we call the centripetal force. The FC, that's what to bring about. Now, don't forget what the centripetal force is. We derive a couple of formulas for that. I'm going to take off this portion. Now this is it here. Now the force of the centripetal force is simply mass times centripetal acceleration. Centripetal acceleration or angular acceleration or radial acceleration. So simply mass times mv squared over r. We all know this is very common. This is very common one. We use this to derive our formula for escape velocity. This escape velocity here, the velocity that the velocity with which a given satellite moving about the Earth will break out of the orbit with. You understand? So now, apart from for the fact that the acceleration is v, don't forget this angular velocity times linear velocity. And don't forget that the linear velocity is angular velocity times radius. Now, if that is it, it means we could also have another kind of formula whereby the v will substitute into this place angular velocity times radius times angular velocity, which is angular velocity squared times radius. So we could also have this, and so it means the centripetal force is same thing as mass times angular velocity squared times radius. This centripetal, force. Now, centripetal force sometimes, is being balanced according to Newton. For every action, there's an equal and opposite reaction. So it's been balanced by a fictitious. So when we talk about a fictitious, we're talking about a kind of imaginary force known as the centrifugal force. No, you're not going to be digging deep into that. So centripetal force, when it's been balanced with what we call the centrifugal force, is the same thing as the mass times angular velocity squared times radius. I also have another formula. Don't forget that angular velocity is 2 pi frequency. Now frequency is 1 over period. That's what frequency is. So the angular velocity is 2 pi times 1 over t, 2 pi over period. And don't forget what the formula for period. The formula for period derived in the previous class is time over number of oscillations. And don't forget this, there's a fact. It takes, the Earth 24 hours to complete one full cycle. So when we talk about the time, the period, for one complete revolution to be made by the Earth, it is simply 24 hours over one cycle over one, 24 hours over one. So we're going to be looking at that later. So let's just quickly complete the derivation of these formulas. So what do we have? What we have right here is simply this. The centripetal force also could be the mass times 2 pi over period raised to power 2 times radius. So we have centripetal force equals to mass times 4 pi raised to power 2, 4 pi squared over r over square of the product also. This is another major formula for the centripetal force. So you're going to be using all this, under the gravitational field. So now we have this. Now let's finish up the derivation of this formula. We're talking about the body at the pole. Let me just quickly take it, give out the diagram again. There's it here. This is how the Earth looks. At the pole, the Earth is flat at the pole, while it bulges at the very edge, where you have the equator like this. So somebody standing here is different from somebody standing right at the equator. So we talked about that already. Let's say there's a center. So now let's look at this. The force of gravity is going to overcome the weight of this person. If gravity doesn't overcome the weight of this person, then this body will not move, will not, continue moving around the Earth in this very orbit. It's not going to happen. So the force of gravity is going to overcome the weight, which will bring about the centripetal, force that we're talking about. So what do we have now? Force of gravity minus the weight. Weight is mass times gravity. We're looking at what's going to happen at the pole. That's what we're looking at. Now the force of gravity is what? It's simply mass that we have here. This is mass times angular velocity squared times radius. Now what's the radius? Radius is simply, I say radius, I mean the distance. This represents the distance. What's simply the distance? The r is the distance, not just radius. The r is the r there represents the distance. So what's the distance at the pole between this very person, and the North Pole? There's no distance. The distance between the two of them is 0. So because this person stands directly on the North Pole. So if the distance is 0, it simply means the mass, whatever the mass of the Earth is, the mass of the person, times angular speed times radius, it means centripetal force over 0 Newton, because there's no distance between the person standing and the spot. They are just directly in contact. So what do we have? It means at the very poles, either north or south pole, it means the force of gravity, just hand this over, is equals to mass times gravity. So what means that the force of gravity is equals to weight at the very pole. At the very pole, force of gravity is equals to weight. So quickly, we are going to be looking at what the force of gravity will look like at the equator. Now let's look at that. at the equator, what would the force of gravity be at the equator? We're done looking at it at the pole, so we've got to look at it at the very equator. So the force of gravity at the very equator is still going to be the same thing. It is the force of gravity that helps this body to keep moving in the circular path. Force of gravity brings about the centripetal force. So now at the very equator, there's it here, at the equator, at the equator, the force of gravity is minus the weight. The force of gravity is always greater than the weight. So the force of gravity minus the weight is same thing as the centripetal force or centripetal or angular force. So that's going to be force of gravity minus weight equals to mass times, what we have, the angular velocity squared times radius. Now this time around, the distance between this very body here and the center of the earth is about, let's say, 6370 kilometers. It varies. It's a different distance from here to here. Like from here to here, you look at from the pole. So here it's flat. This is a flat region at the pole. So we're going to have like let's say 635 something, about 6,357 kilometers from this very center of the earth, the equator, to the pole. Well, now we're talking about we're talking about from this very spot right on the equator to the center of the earth. So the distance is going to be something. The distance will not be zero this time around, unlike when the body is directly on the very pole. So the force of gravity minus the weight equals to, that's what we have, is the major formula for, the weight of the body, the weight of the body in relationship with force of gravity at the very equator. So these are the things we're going to be using. We're going to be using this, and we're going to also be using this to solve what we have right here on the board. Now let's go back to the question. So we're done with these are the major formulas I want to, we're going to be using. The other formulas, we're not going to dig so deeply into gravitational field. That's not what we're talking about. We're talking about the circular motion. So quickly, let's solve this very question. Now, suppose the Earth is a perfect oblate sphere, or is a perfect sphere with radius 6370 kilometers. Good. The person weighs exactly 600 newtons. Somebody starts at this place, weighs 600 newtons at the North Pole. How much would the person weigh at the equator? Now, don't forget that at the very North Pole, the force of gravity is equals to weight at the very North Pole. Why? Because there is no distance between the body standing at the North Pole and the North Pole itself. So, what would the person, if you look at the person weighs 600 newton, don't forget the weight is 600 newton at the North Pole, which is sitting as the force of gravity. That's what it is. So 600 newton is equals to mass times gravitational, force. So what's gravity? Gravity is 9.8 meter per second square. So we're going to do that. The 600 newton is mass. We're going to get the mass of the body first. 9.8. Divide both sides by 9.8. Both sides by 9.8. What do we have? The mass is, let's quickly use our calculator. It's going to help us out here. So let's see. The mass would be 600 newton divided by 9.8. So the mass would be 61.2. That's 61.2, that's a kilogram. Don't forget, we have different systems. We have the CGS system, which is centimeter, gram, and second. We have the MKS system, which is the meter, kilogram, and seconds. So everything we're working on right now is based on the system: mass, meter, kilogram, and seconds. So the mass is in kilograms. It's 1.2 kg. That's the mass of the person standing at the North Pole. So that's the mass of the person. So now look at, so if the person weighs exactly 600 newton at the North Pole, yes, we know that. How much would the person weigh at the equator? Simple. How much would the person weigh at the equator? Now look at this formula. The force of gravity minus weight is equals to this. Mass times this, angular that is velocity raised by 2 times radius. We know what the radius is. Radius is 6,370 kilometers. That is well known. So quickly, let me take up this place. Let me bring it down here. Let's make some room. Let me bring it down to this place. I'm trying to get what the person will weigh at the equator. The person weighs 600 newton at the pole. So we're trying to get what the person will weigh at the very equator. So now let's see what the person will weigh at the equator. Now look at the force of gravity minus weight equals to this. Now, the radius stated, the radius is simply the distance. 637 kilometer, that's the radius, we know that. Now, what's going to be the angular speed? The angular velocity Angular velocity is what we're going to get right now. Angular velocity is 2 pi over period. Now, don't forget, when it comes to the F completes one revolution, a cycle, in 1 day. That's 24 hours. So now, if that is it, now it means the period, which is time over number of oscillations, the period is 24 hours over one cycle for the F. So the period is 24 hours. Since what we're talking about is MKS system, we're talking about meter, kilogram, and seconds. We're going to convert this 24 hours to seconds. So how do we convert 24 hours to seconds? 60 seconds make 1 minute, 60 minutes make 24 hours, make a day. So it simply means you're going to multiply 24, 60 seconds make a minute, so 24 times 60 times 60, and then what else? 60 seconds a minute, 60 minutes make 1 hour. So I think that's that times 3,600. So we're going to do that to 24 times 3600. That'll give us 86,400 seconds. That's 24 hours and seconds. So everything is set out. We have a period already. So since you have a period, it means you have an angular speed. That's what it means. So you can easily get that. So our angular velocity, square of it, will be equals to, that's 2 pi raised to, that's 4 pi squared over the period, which is 86,400 square also. So this is what we have right here. So we're going to use our calculator to solve this. So this is 4 times, we have the pi, 4 times the pi. Extreme 2, the pi is 3.142 squared divided by 86,400 squared. That'll give us 5.28 times 10 raised to the minus 9. So the square, that's the angular speed squared. What we have right here is equals to 5.28. That's 5.29 times 10 raised to minus 9. That's what it is. So this is what we have. Don't forget, this is 2 pi over period. So when you square it, square those two sides, you end up with 4 pi squared over the square of this period, which is 6,400 seconds. So this is what we have for the, for the angular, velocity. So after we've gotten our angular velocity, we've gotten our mass. So the distance is already known. Now this distance will not be in kilometer, it will be in meters. Why is it going to be meters? It will be in meter because you're talking about the MKS system. Meter, kilogram, and seconds. Since the mass is a kilogram, the time is in seconds. That's the speed, and that is the period is in seconds, which is taken as time over number of oscillations. So it means the distance also cannot be in kilometers, it be in meters. So how do we do that? 1,000 meters make 1 kilometer. We're going to multiply this with 1,000. So that's what we're going to do. So everything is well set out. We are looking for this. That's what we're looking for. What the person will weigh, the weight of the person. Now, don't forget, force of gravity is the same thing as 600 Newton. We got that already. The force of gravity is 600 Newton. Don't forget that at the pole, the force of gravity is equals to the weight. That's what it is at the pole. So the force of gravity is equals to 600 Newton. So it's high time we solve that. It means this goes here, this comes over to this place. So the weight is equals to, that's the person's weight at the equator. It's equals to the force of gravity, which is 600 Newton, minus all this. So we're going to solve all this first. The mass times angular velocity squared times radius. So what's the mass? The mass is 61.2 times the angular velocity square, which is 5.29 times 10 raised to minus 9 times the distance between them, which is 6370. So we're going to use our calculator to make things very, quick for us. We're going to use our calculator to do that. So 6.12 times 5.29 times 5.29 times 10 raised to minus 9 times 6370. Don't forget, you're going to convert this to kilometer. Times 1,000. I almost missed that. So this in meter is this. So let's quickly use our calculator to do that. So what do we have? We have this. Then 61.2 as our answer times 6370. There are 3 zeros to it. That's a meter. So what do we have? We have 2.06. So we have so it means what we have. It means the centripetal force is 2.1. That's 2.1 Newton. That's centripetal force. So everything is gotten. So now it's high time we got this. So the force of gravity, which is 600 Newton, You're looking for the weight, this column over. So 600 Newton minus the 2.1 Newton. So 600 Newton minus 2.1 Newton will give us 579. 500, that's 589. Am I right? That's 597.9 Newton. It's just it, as simple as that. So the most important thing is, the formula. We can write the formula already. So there's a formula at the equator, there's a formula, and the other formula at the pole is simply the fact that since the radius is zero, it means force of gravity will be equal to the weight. So since force of gravity is equal to the weight, and that's why it was very easy for us. The force of gravity here is equal to the weight that's at the pole. So if that is it at the pole, it means at the equator, it's simply force of gravity minus weight equals to this. Because at the very equator, there's a distance between the equator, the center of the earth, and the very person. So that is that for that. So this is everything for the final worked example. So I would love you to stay back for take home questions that will test how much you've gotten so far in this very lesson. So guys, these are all the questions we have as a take home, to test how much we've gotten from this very lesson on uniform circular motion. So I'm very confident that after the major 7 examples that we're taking on this very lesson, we can handle all those questions. So we're drawing the curtain on today's lesson at this very point. So if you have really been blessed by this very lesson, I would love you to subscribe to the very channel at Edu Mosaic and also follow me on Facebook at Revelation Hub. And please share this very lesson also with others. See you in the next lesson. Thanks.